Hello everyone, this is my video summary for the All of Statistics book by Larry Wasserman. So I'm going to summarize every chapter of it. I'm not going to cover every small detail, trying to give you the big picture. This is basically a video note to myself, and I hope that other people find this interesting and informative. I'm going to upload this on YouTube, but I'm going to link to this on my Roam graph and try to expand any point which is not clear using text, or writings or other people's video and things like that. So basically, this is a work in progress. This is not only a YouTube video. It's going to get more enriched over time. Okay, so starting with the first chapter, which is about probability. So the first question is that why do we need to study probability if the topic is statistics? And for that, we need to think about two abstract concepts. So the first one is population, and the second one is sample. And for population, you can think about, let's say, the US population. And you're interested in, for example, income of people, or I don't know, height, etc. And these are random quantities. We are not sure about how deterministically they are determined. Like, how could you exactly calculate the income? It somehow relates to your education, your genetics, your socioeconomical background, and stuff like that. Same for height. And there are other variables that are influencing these two, but it's sort of a random process. There is some underlying random data generating process that determines these variables. And also, we randomly sample the population. And so there is some probabilistic model going on in the population, and there is some probability or probabilistic model of sampling that from population selects some individuals. So from the population, we get some individual. So each of these individuals has their own income, for example, and we have n of them. Okay. And this is my observed data. So this is what I actually measured and observed from the population. And now that data generating process, for example, has some parameter or some quantities that I'm interested in. For example, I'm interested in the average income of the whole population. So can I use sample incomes and estimate the average income and be accurate about it? So this is the topic of statistics. There is this underlying probabilistic model that generates the data and gives us the samples, and the reverse of that is statistics. We need to start with set theory. So, and then probability is going to be the way that we measure sets. So probability is for measuring size of sets. And then, as I explained before, we can go back to statistics theory. Okay. So for set theory, I'm not going to talk about all the basics of set theory, only the part that is relevant to probability theory. So what's the relationship between set theory and probability theory? So probability theory is interested in measuring outcome of a random experiment. So these sets are basically outcomes of a random experiment. Okay, so first we define the set of all possible outcomes. So this is my sample space. So for example, let's say my random experiment is rolling the dice. So the set of all possible outcomes in this experiment is numbers between 1 and 6, including 1 and 6. And I can have, so this is capital omega, I have small omega for each outcome. So this is going to be one single outcome. So for example, so 1 or 5, these are each of them is an outcome. And then you can have subsets of the sample space. And we call this an event. So I like these Venn diagrams. So if you think about it, I have this large set, which is my sample space. And then I have these small events in the rolling dice experiment. And then if I group them together, I get, for example, A1. This can be my A2. This can be my A3. And we know that the size of a subset of a set with n members, 6 members here, for example, is 2 to the n. So basically I have AI, and I can be any number between 1 and 2 to the 6. So these are all possible events. And we have intersection of sets. So A intersect with B is a set of shared members between A and B. We have union of sets. Any member that is in either of these two sets is going to be in the union of them. A minus B, you can generalize that this is the set of all members of A that is only in B and that is only in A and not in B. And we have a complement, etc. And we can use these intuitive Venn diagrams to drive relationship between sets. For example, A minus B. So this is A, this is B, and A minus B is this set. You can easily see that A minus B is A intersect with B complement. So this is the B complement set, and its intersection with A is this area, which is exactly A minus B. So it's an intuitive way of doing set algebra. Now going back to probability, we talked about probability being a way of measuring sets. So imagine that I have this set A, and this set B, this set C, and I want to somehow measure size of A and B and C. So you can imagine that size is a function, and it accepts a set and gives you some number. So this number should be positive. So the minimum size of a set can be 0. So this is trivial and intuitive. And then if two sets are disjoint, for example, A and B does not intersect, so A and B the intersection of A and B is, so the intersection of A and B is empty, then you can imagine that size of A union B, so set of all members of A and B, size of that should be equal to size of A plus size of B. So that's intuitive. So you don't lose size when you sum up A and B that are disjoint. And then we add some arbitrary size for the sample space, so capital omega. We set it to 1. And basically, because sample space has all of the other events, all of the subset of sample space that we call them events, this intuitively you see that the size of those sets should be less than 1. But we're not going to add that. You can drive that. And these are my axioms of probabilities, the 3 axioms. And for shorthand, we replace size with P, which represents probability. So this is probability function. Okay, so P is the probability function. Again, it accepts a set and generates some number between 0 and 1. So we can extend this axiom for infinite sets. So union infinite union of sets. So you can imagine that when we have infinite union, to prevent the size to blow up, probably AI should get smaller and smaller. But you can have countable number of sets and take their unions. And if they are disjoint, if AI does not have any intersection with AJ for I not equals to J, then the size of union should be sum of all sizes. So this is the extension of the second axiom that we need. Next, we have probability theory calculus. So we have some formulas. I'm going to just briefly mention them, and you can easily derive them using these axioms and intuitively picture them using Venn diagrams. You can imagine that size of empty set should be 0. You can imagine that if A is a subset of B, then size of A should be less than or equal to size of B, and so forth. Okay, so for intuition, you can always go back to Venn diagram. For example, I want to drive a formula for A union B. So you see that this should contain size of A, size of B, and then we are sort of double counting this part, and we should subtract it. So it's going to be size of A, size of B, minus size of A intersect with B. Next, I'm going to talk about independent events. So the definition is very simple. So probability of A intersect with B is equal to probability of the product of individual events. So that's the definition. It's very simple. But intuitive explanation, for example, using set theory is kind of hard. So imagine, for example, I have A as event of 2, 4, 6 in the dice experiment. So I roll the dice, and if outcome is any of these 3 numbers, the event A has occurred. And let's say B is 1 and 2. We can calculate probability of these events easily. So 2 out of 6 is 1/3, and 3/6 is 1/2, and the intersection is only 2, and the probability of 2 is 1/6. So you see that this satisfies the definition of independence, because 1/2 times 1/3 is 1/6. Okay, so the definition is satisfied, but what does this really mean? So it's going to be hard to explain the independence of these two events without talking about conditional probability. So I'm going to talk about conditional probability first, and then try to explain the meaning of independence, or intuitive meaning of independence, using conditional probability. So the conditional probability of A given B is defined as probability of an intersection divided by probability of B, and you're assuming that probability of B is not 0. Okay, and we know probabilities are greater, and we know that probabilities are non-negative, so this is going to be greater than 0. So what is this? This basically compares size of two sets. So size of the intersection and size of the B. And it's going to be hard to come up with a Venn diagram explanation of this quantity, because it's not direct measurement of the set. So I'm going to try. This is my omega set, and this is my set B, and this is my set A, and this is the intersection. Okay, you're saying that size of the intersection divided by size of B is the conditional probability. So it's like you know that B already has happened, so you're just focusing on parts of A that, given that information, can happen, which is just this area. Okay, and you're comparing this set, size of this set, with size of B. Okay, now going back to the definition of independence. So if you have independence, so if A is independent of B, that's the notation. We have P of A, P of B, and then you divide it by P of B and cancel these out, and you get P of A. So what's the intuition here? So it's hard again to come up with set theory intuition, because now we're talking about ratio of size of sets. But if I add probability of omega, which is my sample space, and I know that its measure is 1, now I have two ratios that are equal to each other. So I'm saying that without any information, without any knowledge of B happening or not, I have this ratio comparing A, size of A, and size of the sample space, which is 1. And then after getting some information about B, for example, we know that B has happened. For example, here I know that this set has occurred. The probability of intersection divided by probability of B is going to be unchanged. then the probability of A happening is A intersect with B, because B already occurred. So that's the only part of A that can happen. And if you divide size of this intersection by size of B, this ratio is the same and is unchanged from probability of A divided by probability of omega. So basically, knowing things about B is not going to change the ratio. And it's like the uncertainty about things remains the same. So this is the meaning of independent. If you want to go beyond algebra and beyond the definition of factorization of the probability of intersection. That's one intuitive explanation of independence. So next I'm going to try a second intuitive explanation of independent event, and I'm going to use independent experiments. So independent experiments as a way of doing this. So imagine that I roll a dice once and I get 2, and roll it a second time, and this time I get 3. So intuitively, these two experiments do not affect each other. So the outcome 3 is not depending on the previous outcome. Okay. And what's the sample space for this? So the sample space is, so I have pairs of outcomes, and each one of them has a probability of what? Now I have 36 outcome, so probability of each one of them, so each I and j, so probability of I and j is 1/36. And that's because I assume that they have equal probabilities. And now how can I compute the probability of first outcome? So what's the probability of observing 2, for example? So this is my sample space. And remember that I had 2 experiments, but I can think about them as this super experiment that has 2 parts. So the outcome are pairs like this, and I have 36 of them, 6 times 6. And now I want to compute probability of events. So one event is what I have over here. So this is my event A, and here it is. So probability of this is going to be 1/36. I'm going to think about 2 events in this sample space. So the first event is the probability of observing 2, 4, or 6 in the first experiment. So what is this? So this is a set of outcomes. So 2, whatever, 4, and 6. So if I want to show this, it's going to be these rows. And next, I'm going to define another set, which is second experiment outcome is less than 3. So this is going to be whatever, 1, and 2. So this is going to select columns like this. And finally, the intersection is these. So let me select another color. Okay. And and intuitively you see that probability of A, probability of experiment 1 giving us 2, 4, or 6 is what? 3/6, 3 rows of 6 possible rows. And for B, it's 2 columns of 6 possible columns. And their intersection is what? 2 times 3. So these are like the 6 possible intersections divided by 36. Why? Because we have 36 possible outcomes and they have equal probabilities, and we're looking at 6 of them. So if you look at this, you see that this satisfies the conditional independent probability. So probability of A intersect with B is probability of A, probability of B. Finally, let's look at the Bayes theorem. So imagine that I have this event B that has occurred, and I have set of events AI that satisfy this and I have set of events AI that partition the sample space. So union of all AIs is the sample space, and AI does not have any intersection with AJ. So visually, I have my sample space, I have partitions. So this is my A1, A2, and let's say K. And then I have this event B. Okay. So I know that event B has occurred. Now the question is, what's the probability of, let's say, A1 or AI given B? Okay. So going for definition of conditional probability, we have probability of intersection divided by probability of B. Okay, now I need some other form of conditional probability. So remember that P of A given B is P of A and B divided by B. I can write it the other way. P of B given A, it's again P of A and B divided by P of A this time. And I get this combined formula, which is probability of intersection can be written as probability of one event, A, times probability of the second event given the first event. And the first event can be either of the two, so probability of B given times probability of A given B. So it's like I can factorize, I can write in a product form probability of intersection. So I can do it here and get probability of B given AI, probability of AI divided by probability of B. Because the set of A's partition the sample space, so I have B intersect with each of the partitions. And these are disjoint. So I can write B as summation of some disjoint, summation of probability of some disjoint events. So basically these are AI intersection with B. Okay. And I can use the same trick and write this as probability of B given AI, probability of AI. And because I've used I over there, I'm going to change this to J. So index them with J. And now if you put together these two, you get the full Bayes theorem. So probability of AI given B equals to probability of B given AI, probability of AI divided by summation of same or similar terms. Now, why Bayes theorem is interesting? So this is a well-known example. So let's assume that we have healthy people and diseased people, and these partition the sample space. And we have a test. So this is my test T. And I want to answer this question. What's the probability of disease given test? And let's assume by test we mean test equals to 1. So the test result is positive. Using the Bayes rule, I can switch the place of T and D. And then I can write the denominator using the same quantities. And the interesting thing about this new formulation is that you can estimate everything in the right-hand side using data. So you know the frequency of the disease. So this is the frequency of the disease in your population. You can just look at how many patients you have with this disease. And then you can test those patients and see what's the probability of these tests coming back positive. So again, you can compute this using data. And also you can take healthy people and run the test and computing the false positive. So if the test is positive, but the person is healthy, this is false positive. You can also compute this using data. And same here. And then using data and Bayes formula, you can compute this. So what is this? So this is for new patients. So I don't know definitely that this patient has the disease. For example, for COVID-19, we have patients with lung problem. So we know that for sure because of their X-ray, for example, they have the disease. And we have a blood test. So this is our blood test. So this is our blood test. And we're not sure how accurate this blood test is. We're going to use other information like lung X-ray and things like that to come up with numbers, exact probabilities in the right-hand side. And then you can say, okay, so what's the probability of COVID-19 given that blood test is positive? Now we can compute this probability. And now you can be confident about the test result or not. So if this number is high, so let's say this is very high. If the if the blood test is positive, then you're very confident that your patient has COVID. So that's an elegant way of computing this probability using data, and that's why Bayes' theorem is useful. Yeah, so this was my summary of chapter 1 of all of the statistics book. It took me longer than I expected, so probably I'm going to be more concise in next videos for future chapters. And please give me your feedbacks and comments. Thank you.